Swayamprabha. Digital India. Educated India.
Good morning again. At the point where we left off last week, we were talking about the difference between probability and probability density, how probability can be the theory of probability, or actually the whole concept of probability can only be applied to where the number of outcomes is finite and countable, whereas you need to go to a concept like probability density when the outcome is on the real axis. So, any real number between some limits is a possible choice for an outcome. Okay, so, without going much into the theory, and this is actually an unresolved question in space, we will for now assume that drops can be any size between some minimum size and a maximum size. Okay, the minimum size could be 0, the maximum size could be infinity for all we care, but we will just assume that they do have some finite limits, and even otherwise nothing in what we discussed the other day is going to be different, as long as there are some limits on which these two on which all the drops exist. Okay, so, we will continue that discussion. And start looking at sprays in some detail. Okay. So, we know that we define a PDF So, f of x is a function and f of x times dx is the actual probability of finding the value in the range x to x plus dx. So, that is if this f of x is defined in this fashion, then f of x is called the probability density function. Okay. So, this we looked at the case the other day when we looked at a circular hoop, and we said what is the chance of one of the angular positions showing up on top, and really speaking the probability density could be any value. In fact, the probability density does not have to be between 0 and 1, because this is the actual probability of any set of outcomes has to be between 0 and 1, but the probability density itself can be any number. We will see in a short while. Okay. In other words, the function has no upper limit on the values that it can take, as opposed to probability. Okay. Fine. So, applying this principle to sprays, what sort of intuition can we bring to the forms of the function that this f of x should have in a general spray? Let us start thinking about that for a little while. So, if I will now use a slightly different notation, I will say P of D P of D is the probability density function of, say, a drop diameter in a spray, and I will be even more specific, we will just say at a point for now, at a spatial point. So, this is sort of the easiest to understand. So, we will start with this. So, if I did my temporal sampling, so I was sitting at one point in the spray and I sampled every drop that went by me, and I accrued statistics of a large number of drops, and we discussed how to construct a probability density function from a large set of such drops. Okay. So, I did that and I got this function p of d, p which is a function of d. What sort of functional forms, what should the graph of p of d look like? So, if d is generally speaking, what would you expect the graph to look like? Let us draw some simple features. The first sort of physical limitation is that the drop size cannot be less than 0. Correct. So, on the right side, on the left hand side of the graph, the probability density clearly has to be 0. Now, can I find a drop of size 0? There is no such thing as a drop of size 0. The drop is of size, say some minimum possible size in the spray. Now, we will see that we will see maybe in a couple of classes from now that number is actually a number that is much greater than 0, much in the sense of atomic scales. So, if one molecule of water is a few angstroms, the drop of water, the smallest drop of water that you can create using a spray process will be much bigger than this size. Okay, and there are reasons for that, we will talk about that, but let us for now say there is a d min below which I do not expect to find any drops. What about a d max? Let us talk about the limits. If I take a typical spray, we looked at the perfume spray in some detail, there is a hole through which, a hole on that perfume can through which drops are delivered into the spray, right. Now, is it reasonable to say that there can be no drop bigger than that hole diameter? So, in other words, if I have an injector diameter, I cannot produce drops greater than that injector diameter. Okay. Strictly speaking, I am wrong. I can produce drops greater than the diameter if I have other processes going on later on. So, if two of these drops want to come together and coalesce, I have no reason to prevent that from happening. So, technically speaking, there is, I cannot say that I cannot find drops greater than that size. All I can say is the probability has to continuously decrease as the size decreases, as the size increases. So, as the size, say for example, if this is my orifice, okay, all I can say is as I go further away from this DO, this probability has to somehow decrease. So, that is going to have to be the form of the graph going away, it has to asymptotically reach 0. Okay. Now, this is as far as our understanding without really having a spray in front of us, no data, nothing. Say, now, can I actually allow this graph to come intersect? So, if I is this a reasonable possibility that the graph will intersect this axis? Beyond that, the answer is that there are no drops greater than that particular size. All I can say is I cannot make this generalization for every spray. So, at the moment whatever we are saying, We want to leave it sufficiently flexible to be able to apply to every spray. Okay, that is sort of our approach for now. Okay. So, at the moment all I can say is that this has to asymptotically approach the diameter axis. So, the probability density asymptotically becomes 0. What about the shape in between this and this? Now, first of all, I know the shape of the graph near d min, it has to increase, that is the only way it can go. Probability density also, by the way, cannot be a negative number, right, just like probability. So, probability density is a positive number with no upper limit, lower limit is of course 0. So, with these as this thing, now I can, there is only one possible general shape for this graph. If I say this is the starting and that is the ending, there is only one way the graph can go, which is if the probability density function is a continuous function and differentiable everywhere, this is one possibility, which means that there is one point which is the, at which point the probability of finding a drop around that point is the maximum. This is not the average drop size. So, we will look at that in just a moment. This is the what we will call the most probable drop size. So, you can sort of just, although this is not a widely used way of referring to it, we will very soon make the distinction between average and this most probable. Drop size. But so essentially I have this function p of d, which could be, which now has these general features. If I want to write a mathematical equation that fits this, there are many different mathematical forms that are possible, that initially increase and then decrease, okay, with or without, with d min being 0, with whatever it is, there are many mathematical forms that are possible. As many mathematical forms, so many proponents in the literature for those mathematical forms, meaning this is, there is at least like 5 or 6 very widely used forms of distributions that people claim are fundamental to sprays, and each of them has their own valid reasons for those claims. So, this is, but this is the shape that is generic to all of those mathematical forms. We will come to that in the next class, but before that I want to define a few parameters that are not dependent on the specific mathematical form. Okay. The whole point is that ultimately if I say what is it that I have achieved by defining this, I have defined the spectrum of drop sizes that I can encounter at one point in the spray over some period of time. How useful is this? Very useful, because I now know what the spray looks like from the inside, like we said before, right. But in many instances this is too much information, I want to condense it. If I have to now move to another point, I have to find this all over again for that other point. Okay. So, I want something that is more manageable, and therefore, going from this full, this is the full probability density function, we want to define what are called moments of the distribution. Okay. The simplest moment to define, before we go to defining moments, I want to make one obvious point one more time, that if I take any of these, the area under this the area going 0 to infinity of that probability density function in dd. It is a little tricky, but I cannot help it. I can probably make the point over here as well, just to sort of, because integral 0 to infinity f of x dx, because f of x dx is a probability of finding the point in the set of outcomes x to x plus dx. If I do this addition over all the x, that amounts to integration, and that is what I get. Okay, this is the only requirement of any probability density function. All right. So, I now want to define a set of moments of this. The simplest is what we call the average diameter. I will move away from this dd business, and I will say moments of a PDF f of x, okay, and I will define x is drop size in this case. Okay. First constraint is that f of x dx equal to 1, and then if I define a mean drop size, let me write down what this is. So, the probability of finding a drop in the limits x to x plus dx is that. So, that probability multiplied by the drop size itself, added over all of the various sizes possible, is what gives me the mean drop size. Okay. So, just to sort of illustrate the point, if I have, let us say, different sizes xi, x1, x2 dot dot dot, some xi, xn, I have n drops of sizes, then the mean drop size for this sample we all know would be x1, x2, that all you are saying is that each drop has a probability 1 by n. So, you are essentially multiplying 1 by n times x1 plus 1 by n times x2. Now, if x1 and x2 were the same, for example, in this set, then that would become 2 by n x1, 2 by n x1, because you have 2 drops of size x1. So, essentially what we do by average is the same as what we are doing in the sense of probability density. Now, we are going to get used to this notation of using the angular brackets to denote mean. So, this is often called the first moment. I can define any moment of this distribution by doing exactly that. Okay. So, if I take x power p, p could be some number, then x power p, just like if I have drops of size x 1, x 2, x 3 etcetera, then I can define x, if I say what is the average surface area of these drops. If I choose p equal to 2 in this case, that gives me the mean surface area, barring some factors like pi or pi by 4 etcetera, that does not, I mean, we are not really worried at that level of detail, and we are not concerned about that also usually. If I choose p equal to 3, what do I get? I get the mean droplet volume. So, I can define any of these moments, I can define a p equal to 4. Now, what would that physically mean? I do not know, but I am sure there is a reason to define it, and people actually use it. We will see in a moment one such use. Okay. So, what we want, and by the way, p equal to 1 gives me the number based average. So, if I set p equal to 1, that is simply the mean diameter. Okay. I can define an average called x p cube from this same f of x as the following. So, if I say x power p f of x dx integral 0 to infinity divided by x power q f of x divided 0 to infinity. If I raise this whole thing to the power 1 over p minus q. Let us think about what this is. X power p, this is the pth moment, and the numerator is the pth moment, the denominator is the qth moment of this same distribution. If I take the ratio of the two, that gives me sort of the value of the pth moment in comparison to the value of the qth moment. That is essentially what ratios are. But the funny thing is, if x has units of say micrometers or millimeters, x power p has units of millimeter power p, x power q has units of millimeter power q. So, this ratio will actually be a dimensional quantity of units millimeter power p minus q, which is like a funny unit. I do not want to deal with that. So, if I raise this whole thing to the power 1 over p minus q, that gives me something in the units of diameter. So, this is also some moment of the droplet size distribution, and is a diameter, and it has the same units as diameter. So, I can now relate to it physically. That is the only reason to do the power 1 over p minus q. Let us look at some simple possibilities. If I set q equal to 0 and p equal to 1, we get our first moment. P equal to 2, q equal to 0 gives me the second moment, just the way we have defined. But if let us say p equal to 2 and q equal to 1, what do we get? Raised to the power 1 over 2 minus 1. So, this is essentially the mean surface area divided by the mean diameter. Okay. So, going back to our original this thing, I want to now write everything in terms in this PQ notation. X10 is the mean diameter, you can see that. X20 actually, let us be clear about this, I am sorry, we will say this is the mean so just simply a number based diameter, okay, because I am just doing an arithmetic average of all the drops, that is essentially what X10 is. If you go back, look at this notation here of XPQ. If you look at this notation of XPQ, the numerator is xf of x dx, which is just like saying I am doing an arithmetic average over all the population of drops that I have. X20 is the mean surface area based diameter, and just for the sake of equivalence, I am going to do a 1 over 2 minus 0 to make it look like a diameter. So, I have taken the mean surface area in the spray at that point and divided and taken the square root essentially to give me back a number that has units of length of size. Okay. Likewise, X30 so these are all diameters, that is the point to note here. They have the same units as diameter, but they are all different physical quantities, because now the X30 tells me sort of the average volume. So, it tells me where the volume is concentrated. Another X 32, I want to write this out. Okay. Now, this has a special name. This is often called the Sauter mean diameter. Now, when you see Sauter mean diameter in the literature, they do not use x, they use d for diameter. I am just using x because that is easier to do dx and these kinds of notation. But imagine D32, you will see this written very often, D32 is this outer mean diameter at that point in the spray. Now, this is very widely used as a measure of a spray. Now, remember, it is just another moment of the PDF, that is how you get this outer mean diameter. But what makes this number so special? It is essentially the fact that the numerator is the mean droplet volume and the denominator is the mean surface area. So, both those quantities being physical, if I want to imagine a situation where I want to release the volume contained in a liquid drop into a gaseous medium, it has to go across this interfacial area. So, any sort of a mass transfer problem, that is the simplest to imagine, but it also applies to heat transfer. Any sort of a interfacial transfer problem involves volume, because that is your source of either mass or thermal storage in the form of rho Cp, rho Vcp or Mcp, that is the total thermal inertia or thermal storage capacity of a given drop. So, that M or rho or M or V is an indication of the volume in the which is in the numerator, and the denominator is what the mass has to go through, the total interfacial area that is available to a certain given drop for that mass to become, let us say, evaporated or heated or whatever interfacial process has to happen. So, this is essentially also referred to as the mean, this is essentially like a mean volume per surface area for the drop, or 1 over this is the mean surface area per unit volume. You know, in our very first lecture we said the whole objective of a spray is to increase surface area. Here is a direct measure, surface area of what? Surface area of a given volume of fluid. So, here is a direct measure of that increase in the surface area per unit volume. So, if you in some very crude way take 1 over this and multiply it by your volume that you had in that one whiff, that automatically gives you the total surface area that you have generated. Okay. So, that is this is one of the more commonly used measures. Another sort of commonly used measure is called the de Broglie diameter. Okay, notice that if P minus Q is equal to 1, and automatically you have units of diameter. Okay. So, this is used in cases where in like spray drying, where evaporation is important. So, it is like x square gives you the surface area and x power 4 is a moment that is related to it, although it is really speaking outer mean diameter is what you will see reported in many different applications. In fact, some of this theory of handling distributions came about even before they had the idea of characterizing sprays using distributions. The first origin of idea of distributions came from pulverized coal. When power plants, when coal fired power plants were being built, the most it was figured out that the most efficient way of burning coal was to pulverize it to tiny particles and then burn it. So, I now had to have some measures of the what the result of my pulverization process. So, all of these distributions, all of the moments that you see here D20, X32 or D32 were all developed for particle sizing in coal in pulverized coal applications, and they are just as applicable for this case as well. So, here we have what I am claiming now is that using, let us say, I will start to number this just to give you a quick count of where we are. Let us say there is 1, there is 2, there is 3, I will also add x to 1 here, which is the mean surface area per average drop. So, how much? So, that is like another measure of surface area per average diameter. There is 5 and there is 6. So, we are now somehow claiming that instead of giving you a whole PDF, if I give you either these 6 numbers or even a few of these 6 numbers, you can get a reasonable estimate of what that distribution will look like without really having the full functional form at your disposal. Okay. Knowing the limitations that we started to talk of. Okay. If I just tell you an x20 and did not tell you it was from a spray, you really could not make much of it. If I tell you it's a drop size distribution, then you already have all this intuition that we started with, that the drop size distribution has to tend towards smaller and smaller values as you go forward, as you go towards infinity. It has to have an almost finite cutoff, although d min can be 0. There is no reason to not be 0, but we usually find it to be a finite value, and it has to reach a maximum value at some point and then drop off. This intuition taken alongside that number now tells you some shape of this distribution. Like for example, I can clearly say, I mean the simplest intuition to start with is to this would have a greater x bar. You can already see that. So, if I just tell you x bars of of the spray at 2 different points, you can imagine what these distributions would look like. They have to be something like this. Now, spray itself is not a one dimensional entity. In the sense, I am not talking spatial dimensions or time. The set of drops at one point in the spray are characterized by more than one variable. We looked at a whole list of variables in the very first class. So, I could have diameter be a characteristic, temperature is another scalar characteristic, concentration is another scalar characteristic, velocity is a vector characteristic. I can treat the velocity as being, let us say, at most 3 more scalar characteristics, scalar properties. So, I could have all these scalar properties of a drop apart from the size itself. So, if I want to understand what the set of drops look like in that space, I need to go to multivariate distribution. Say for example, I will simply